Buenas tardes.
Hola, hola.
Profe.
¿Hay preguntas? ¿Dudas? Bueno, no está en su boca, no hay. Ok, vamos a comenzar. Ok. Entonces, vamos sobre como ionization losses. Y now I'm going to return to something a little bit more out of the book, out of Rebecca Enlightenment. And so just to frame everything, to come back to lecture 3A, we were talking about tensors and the four potential. And so we developed this thing called the Faraday tensor. Yeah. And so the Faraday tensor is the difference between the contravariant and the covariant potential. And so it has this interesting sort of off-symmetric or anti-symmetric non-vanishing terms, right? And so when you sort of formulate Maxwell's equations, you can formulate them in a very super compact form. And then a conservation of charge equation then looks something like this, right? So taking the derivatives of this. Okay, so recalling that, we just want to, we can actually, if we write this all out and think about a moving charge. So we have a charge in one frame and we can characterize its electric field in that frame as a function of radius and of each position. And so this is fairly simple, just Coulomb's law. So when we transform it into the K frame, we then have interesting consequences. So in the X direction, there's the transformation is okay so far. And we have extra terms that come from transforming the Y and Z directions. We get this perpendicular component which materializes in the B and Z directions, right? And then when we take the Lorentz transform of X prime and put it into X, then we end up having the transformation come here. But it also comes here. So when we transform from R prime to R, we have this extra factor here. So the gamma factor and the V come in here. And so they actually are in here, in here, in here, in here. Right? Even though the Z and the Z transform pretty trivially. And so the full-blown transformation from our standard Coulomb's law in the rest frame to the observed frame, moving with some velocity, ends up having these extra terms, right? So this is how you would see it. Okay, so with that, then we can look at what happens. We have a charge that's moving, and we initially had calculated the Leonhard-Warkhardt potentials for this delayed or retarded time, right? And we had seen that had ended up sort of manifesting in some sort of power which went as 1 over R. Right? So we had, actually the field went as 1 over R, whereas the Coulomb field should go as 1 over r squared. So we had a field which appeared at large radii to dominate. And so what we want to do is take the classical derivation that we've done before with small velocities and do the same thing now with our relativistic velocities. And so we have the same setup here that we had before. So we have some charge which is moving, and so it is giving off a field, and we want to see what is the field at this position. And so it's a position r away. And by the time the field travels to us, this electron will have moved some distance, right? And so we want to capture this. And so this delayed time is related to the time minus this distance it needs to traverse. We have r squared, which we can separate out into a y component and an x component. And the x component actually is going to be different by this extra distance here. And so we can plug in this here, and then we end up getting this. And through a substitution, so we substitute and put x average here for x minus vt, and then moving around various bits and pieces, we can derive r as a function of gamma of this thing here and x and y. And we can also write a unit vector. And so the unit vector will is going in this direction of r. And so we can derive a sort of y component and an x component of that unit vector. We also have the beaming factor, which we had before, and the beaming factor was defined as 1 minus this unit vector cross product with the velocity. And so now we have the unit vector looks like this, and so if we do this cross product, we get this beaming factor will end up looking something like this. And so it has sort of a factor of gamma in here, but this will sort of cross out depending on how strong this is versus this. Okay, and we still have the beaming factor, I guess, in this big R. So this is the relativistic version, is just the fact that this the gamma factor creeps in a bunch of different places, and we want to see what the effect of that is. Okay, everyone with me so far? Okay. So we can, if we write this kappa to the third power, this kappa to the third power will give an E-like dependence, meaning it has a dependence of 1 over r cubed. If we go in the z, basically z equals 0. And so if we have something that looks like this, then this thing, if we do all the substitutions, if we substitute in what we had here for kappa here, we end up with something that looks a bit ugly, but looks like this. So this thing has, I guess, the extreme sort of properties that we want. It should revert to a Coulomb sort of field if we have no velocities and so forth. So if this is a 1, this is 1, then we have this thing. If we don't have any sort of motion, then this goes back to x squared, and we end up with, let's see, this should be right. Yeah, so this would be r, this would be r to the third, and so we end up with q divided by r to the square. So we should end up returning back to Coulomb's law for the sort of idealized case that we don't have any relativistic different frames, anything like that. Okay, So we can then think about how we can get the electric field. And so coming back to this, we have this thing here, which is the electric field in the x direction, the y direction, the z direction. But in particular, we want to look at the x direction here. Actually, we want to look at the whole thing, sorry. So we want to have the vector. And so this vector E will end up being, we have the vector, unit vector here, we have the vector of the velocity. And so we can multiply this by this factor here. We have the k3 here and this r squared here. And so this is how how we could derive a E field vector form. And this should end up matching this if we were to plug everything in. Okay.
I have a little comment here. I feel that the term 1 minus beta squared is gamma to the minus 2.
Is this thing,
Yeah.
minus 2. Yeah, let's see. Yeah, I think you're right too. And of course, that it goes down here as that. So yeah, let me fix that. Ah. Very nice catch. Okay. Right. So, but evaluating each of these components out, we end up with something that looks like this. And so the main differences here from this thing are what? So we have this r cubed here, and that ends up being this thing. And we have this x, if we have it at 0, then this ends up looking like this. Right? So if we initially have x0 and we have y at some impact parameter b, then this is what this will end up looking like. And so you can start to see where we're going with this because we have this impact parameter, and we're now going to integrate over the impact parameter and so forth. And so we have a situation that looks now like this. And so we have the moving charge, we have this time delay, we have an impact parameter B, and we're looking at the E fields and the B field in this sort of situation. And what we've done is just by symmetry, sort of given this, just in 2 dimensions. Okay, so in this case, we have this component in the x direction, we have this component in the y direction. They're sort of almost equivalent, but not quite, because we have a VT term here and we have the B term here. And then we have a Z component of the B field, which is proportional to this thing. Okay. So if we have very large gamma, this is going to be equivalent to beta equals 1, and then we have the E and B fields are equal. And so if we think about the different terms, what's going to happen is a function of time. And so the EX field will look something like this. And so it has a maximum which happens at about Q divided by B squared. And so it will have a maximum here, a minimum here, that'll be about equal. So by symmetry, it will cancel out as this charge is passing by some random point here. The Y field, however, will only have one component. And so by symmetry, it will end up actually having some component. And this is, of course, the component in the perpendicular direction. And this maximum that it will have will be proportional to Q gamma divided by B squared. right? And we can just see more or less that at t equals 0, which is where this this will drop off, and then this will have b divided by b cubed, which will be b squared, right? So we can see that. Okay, so the width of this pulse will roughly be equivalent to b divided by gamma v, as we had sort of calculated before. And so this is the situation that we have. So depending on what gamma is, the higher gamma is from 1, right, that's going to increase this signal in this direction. It's going to increase the E field in this direction. And it's going to narrow the width of that. And so if you have something that approaches C, then gamma will approach infinity. And so you end up having almost a delta sort of spike here. And that, of course, is when we actually approach C, then that's what light is, as we mentioned before. Okay. So we have a field that's generated from this charge which passes by. It gives you a pulse of this electric field, which is, we can frame it in terms of a pulse of radiation, which is traveling in the same direction. Basically travels in the same direction as the charge, but it's confined to a transverse plane. Right, so the pulses go, the electric field goes high in this direction, and this is akin to radiation traveling in the same line as the electron, where the amplitude of the radiation is in this direction. And so this connection between the two, or this sort of apparent approximation, is what we call the method of virtual quanta. And so we'll use this later on to simulate what light would look like if we had a particle which was going essentially at the speed of light. Okay, so what we want to do now is determine the spectrum of this virtual pulse. And so we need to do our trick with Parseval's theorem, where we do the Fourier transform. So we have some E field we want to understand as a function of frequency. And so this is proportional to the E field. And now this is not necessarily in the Y component, but in the E2 component as a function of time. And we multiply by this complex E value here, and we integrate it over all time. And so plugging in what we would have for our EY here, right? We plug in that we can move some of these out, which aren't time dependent. This has a time dependence, and this is not a pretty integral to do. It turns out that we need a first order Bessel function, or first order modified Bessel function to deal with this. And so this integral turns out to have this sort of form. So this Bessel function, this modified first order Bessel function, with this as the sort of pre-parameter or index, or whatever you want to call it. And so this is the end of this integral. And we can think of this, this electric field as a function of frequency. We can look at how much energy per unit area per unit frequency that is, and that should be proportional to the square of the E field, well, the square of the E and the B field, but in this case, just the square of the E field multiplied by C here. This is just the, I'm blanking on the term now, the Poynting flux. So this Poynting flux, if we just square this thing, gives us this. So we have lots of constants, this sort of pseudo variable here, which is the frequency divided by the speed and the impact parameter squared, and then the Bessel function squared. So what does this look like? So this Bessel function, so this is a 0th order Bessel function. This is a first order Bessel function, second, third, fourth, fifth. So you can see what the functionality looks like. This plot is not the greatest plot, but it gives you a sense of this. So it has a sort of pseudo exponential or a pseudo parabolic form, if you will, but it's not quite that. But that's the sense of it in terms of how it goes as a function of this x, which x is now this. Yeah. Okay. So we have this thing, and we want to look at the how this actually behaves in a few different extremes. So the spectrum will, in particular this spectrum, will end up cutting off when the frequency gets above this thing. And this can also be predicted by the uncertainty principle, but what it means is that the pulse is confined by a given time, a given interval here. And so we should have a cutoff which is proportional to that, or proportional to the inverse of that. And so if we want to understand this complete behavior, then we can estimate it just within at least a factor of 2 here by looking at the behavior of this thing. And so this thing has a maximum of this over a time interval of this. And so this thing here should be proportional roughly to this. And so we can estimate what the width is and what the maximum is. And so it's the combination of these two things. And so roughly speaking, then this will end up, this thing, the delta width will be proportional 1 over delta time. And so it should be like that. This is just to give you a rough sense of the limits of this spectrum. So we now want to play the game where we integrate over some cylinder, right, with some impact parameter b, some dB, and we find out what the total spectrum is. So the spectrum per unit area, we have y equals b, and so we then integrate over some infinitesimal area, which is, we consider 2 pi b dB, right? And so we want to integrate this between some b min and some b max. And we can't have the b min be 0, we can't have the b max be infinite. And so we choose some values that are sensible. And so we want to, this minimum b will be sort of an approximation using either classical EM and the size of a point charge. We want to make sure that it remains valid. So one option here for b min is just the radius of the ion. If the field is from an ion. The second one could be set based on the Compton wavelength of the particle. And the Compton wavelength would be of order, the Planck's constant divided by 2 pi mc, where m is the mass of the particle. And so in this particular sense, we plug in our value for here. Whoops. There we go. Okay. So we have this lovely integral between x and infinity, where we're evaluating this thing. And here we have a couple of variable substitutions. So y is this, and x is this. And this can end up being solved by a series of modified Bessel functions, which is, again, not pretty. But so we have some constants out here, and I forgot this is velocity. I should have put the actual v there. So this, and then we have a 0th order, modified 0 order Bessel function, 1st order, and then a 1st order squared and a 0th order squared. So this thing is pretty ugly, but it can be evaluated numerically. Just by, we can in a sense, take this and subtract this, or square this and square this and subtract them and so forth. So there are a few interesting cases. And so when omega is really, really small, so omega is much less than this value here, or when omega is very, very large. And so it's much greater than this value. And so in these asymptotic circumstances, this thing will be reduced to a form which is a little bit prettier. And so we have something which looks like this when omega is very, very low, and we have something which looks like an exponential cutoff when omega is very, very high. So this is actually pretty flat and just goes as velocity squared and the charge squared, but doesn't have a strong dependence, right? Because the natural log of something is going to have a pretty weak dependence. So you have something which is pretty flat, and then when you get to high frequencies, it has an exponential cutoff. And this exponential cutoff, again, just comes back to the fact that you have some behavior which is going to be limited by the pulse size. Okay. And so these forms, you could do direct integration of this thing. And this thing has an asymptotic limit of 1 over x for x much, much less than 1. And this thing should have a limit of this thing for x much, much greater than 1. And so that's how you can get back you get out these functional forms. Okay. So that gives us the amount of energy that comes out as a function of frequency for this particular situation. We can think also about a couple other aspects of this whole situation. So we can come back to the form momentum or just the momentum in general. And so this form momentum is a function of this mass and u here. And so this is the velocity now in the rest frame, right? So we choose to have a variable u be the velocity, and then v is the velocity between frames. And so here we have the momentum is related to this velocity, and then you have this extra factor here, this relativistic boost. And you can derive a time component, which looks like this. And the time component then would reduce to something like that. So in each of its components, you would have the time component is mc squared, and then the if you did momentum times c, you would have an energy, right? So you would have the rest energy, and then you have the actual kinetic energy. So thinking about this a little bit more, this first component here is the rest, as I said, is rest energy of particle. If we conveniently square this thing would then look like energy divided by c, and so we can rewrite this as this, and so then this makes a little bit more sense. And so we have E divided by C is this component. We have then the normal X, Y, and Z components of the momentum. So if we square this thing, we end up getting out this, which is equal to this thing plus this. And we could rewrite this, we can move these around, and so E squared is equal to M squared C to the 4, and then C squared times our average momentum squared. Since photons are massless, then we wouldn't be able to define this exactly for a photon, but we could at least use the quantum relations to see how it behaved. Or rather, we would need to invoke quantum relations to actually see how it behaves. We can't use this sort of formalism. Okay. So we can come back to our how we would envision electromagnetic plane wave moving in space-time. And so it has this sort of wave function, which would be the unit vector, or not unit vector, the wave number here, which has some vector cross product with x, and then the time component. And so if we have this thing, this wave has a phase, it should be invariant. And so this means that the E fields and the B fields should be able to transform from one frame to the other, or rather that if it vanishes in one frame, it should vanish in all frames. And so in this limiting case, then we can rewrite this wave vector here, or sorry, the wave number and the time component as this thing, or as this thing. We can have a wave number for vector, which looks like this. And so it would have a time component and a space component. Right? And if we were to take the square of this, or the square of the vectors of this, this would end up being the square of this thing and the square minus the square of this thing. And this should equal 0. Which is just, again, this vanishing, if they go to 0, this thing should equal 0. And so this is how we would reframe it in terms of 4 vector components. This thing we can then think of as being invariant, and we can then use, so we have some arbitrary space-time 4 vector, which is here, and we can, this has some arbitrary wave number vector, which is also a 4 vector. And so we can transform the 4 vector. And so it should transform more or less like X should. And so we have a time component, which would transform like this. We have an X component, which would transform like this. And then the Y and Z components would transform evenly because the frames are moving in the X direction. So this thing would equal this for electromagnetic waves. And this thing, this K component would then look like this. And so when we did a Doppler or a Lorentz transformation of this, we would then have something which kind of reverted to our Doppler formula. And so we would transform the frequency, or rather the frequency in the rest frame to the observed frame would transform like this. And so we have our gamma factor and our Doppler factor. And we have a component which is giving us how much of, depending on how the light is going with respect to the, what do I want to say, the orientation of the frames. Okay. We could then, for the electromagnetic wave, rewrite the momentum vector. So we can, have a quantum relation, which is for, a wave. We have E equals h with h bar times omega. This should be omega, not w, and the momentum could then be h bar times k. And so this thing would look like this for a wave. And so we then, if we had the 4 momentum, this should be null, so that it should be p squared equals 0. And this would then imply that E equals the absolute value of PC. We can also think of a 4 force. And so, we had previously derived the 4 force, which would look like this. And we had a relativistic version of Newton's F equals ma. And so the 4 force looked like this. And that looked like the derivative of the momentum with respect to proper time. And we could split out this, move the mass is going to move out, and so we could define an acceleration, or the time derivative of the velocity in the rest frame with respect to the proper time. If we have this electromagnetic radiation, we can evaluate the force using this Lorentz force equation. And so we have the Lorentz force is equal to the electric component, and then the velocity cross product of the B component. And so we can derive this Lorentz force and equate it to these components of our force. So Lorentz force involves E and B fields. And so if we recall at the start of the lecture, I had shown you the Faraday tensor, which is how we actually, it has the E and B fields and how we transform between one frame and another. And so it ends up being super confusing to see for force and the Faraday tensor. The nomenclature is not ideal at all. And so you have to be very careful about what is what. And so the book does an okay job of it, but there are times when it gets confusing and they don't necessarily make it super clear. Okay, so we have, basically what we want to do is rewrite this for force in terms of a Faraday tensor and in terms of a for velocity. And so this is going to be a little bit interesting. And so we have our for force, we have our Faraday tensor, and we have our velocity. And this is the compact form of this. Right, just taking, we had our, F equals ma and our Faraday tensor. And so we have this u. And so we can end up sort of writing this way. And so in this derivation, the acceleration would be comparable to the Faraday tensor acting on our velocity component with some constants. And just to sort of demonstrate this, we can verify this. So this is breaking down what this is. So this is the vector of the Faraday tensor. This are our individual velocity components. And so what this means, if we take the 0th component here, we have this times this. And so we end up having the E field, right, cross product with the velocity components. Likewise, we can do the first component, and so we do this versus this, and so this ends up giving us, this is the time derivative of a momentum, or for momentum in the x direction. So this would be just Ex plus 1 divided by c, and then the cross product of this just in the x component direction. And so forth, right? So you can kind of see how you get back the Lorentz force, right? But it's at least a nice compact form of that. So this thing ends up being just the rate of change of the particle energy, or the work. And so this is the rate of change of particle energy on the particle by the E field that is there. And this is why it is non-zero. The spatial component follows the standard Lorentz field. So we have this extra component, which is now the field doing work back on the system, right, which we didn't necessarily have before, which we have to take into account. We can also note that this for force should always be orthogonal to the for velocity. And so if we have the dot product of these two things, this should equal 0. So this thing here implies that basically every for force has a velocity dependence, which could be negligible in a non-relativistic limit, but can be substantial in the relativistic limit. And so we can, again, taking this and looking at this in detail, we have this dot product here would be equal to this thing. This is the anti-symmetric version of it. And then we have to couple it with the symmetric versions of it. And so when we apply this and times these two things, we end up with 0, sort of by definition. Okay. Oops. That's all I had to say there. So let's actually continue on a little bit. So we now have sort of things set up to do a transformation of how light will transform from one, or rather the field will transform from one frame to the other in a relativistic way, right? And so now we want to actually try to apply this. So we've set up what the Larmor equation, or the Leinart-Weickart potentials look like for a relativistic case. And now we want to transform it using some of this extra nomenclature. Right, so we want to find out the radiation emitted by a particle moving at relativistic speeds. And so we now, just to clarify things, we have an instantaneous expressed frame K prime, and the velocity, we'll set this up so that the particle has a velocity equals 0 at the start, but has some acceleration. And so the particle needs to remain at rest, but the acceleration can be whatever. And so we have a time interval over which this is happening, which is dt. And then we have the particle here. If this is the case, the particle will be considered to move non-relativistically in its own frame. And so in this small time interval, we calculate the radiation here using the Larmor dipole formula. And so we can denote the work in that frame is dw prime during some time interval t dt, which is the time interval in our frame. If v equals 0, then the momentum equals 0, and then the emission here is going to be symmetric with respect to any direction. And we want to calculate what the energy is in the K frame. And so the K frame is moving at some velocity minus v. And so we do a transform between this work here and the work we see. And we have an extra gamma factor here. And we have the time transformation goes as this. And so dt prime is the actual time of the particle. And so we then can calculate the power, which is dw divided by dt. And you notice that these things will cancel out. So we have that the power doesn't change. So the total power emitted ends up being invariant. And this is true for any source that has a front-back symmetry in its instantaneous time frame, its instantaneous rest frame. And so this is an important quantity to sort of know that the total power won't change. What may change is the solid angle over which it's directed, right? And so you can play off of that, which is what we'll see in a second. So we had our original Larmor formula, which looked like this. And so we want to sort of rewrite it in terms of our new definitions of A. And so in our definition here, we already, we always had that the acceleration should be perpendicular to this velocity, and so the dot product of these would be 0. And so this is akin to this type of forward velocity. So just c and then 0. And this just comes back to our definition of having v equals 0 here at the start. And so we have a time component, this thing, which will end up being 0, 2 in this frame. And so if we evaluate this acceleration, we have an acceleration that looks like this, or that breaks out into the time component and the position component, or that looks like this in 4-vector nomenclature, or this dot product. And so if we think about this power here, and we evaluate it in this frame, this thing ends up looking like this in now our frame. And so this power, because the power, right, the power should be equal, the total power should be equal between these two frames. And so in essence, this thing will reduce to that and should look like this in total. We can re-express this thing in terms of the parallel and perpendicular components as we did before. And so if we go ahead and express this power, we have the 3-vector acceleration. So in terms of this, we initially had that this perpendicular, the perpendicular component will transform, it ends up transforming as gamma squared. The parallel component ends up transforming as gamma to the 3rd power. Oops. And so we plug these in, this thing would end up looking like this. And so we have the addition of the parallel and the perpendicular components squared, the cross terms cancel. And so if we were to plug these in, right, we end up having a factor of gamma here and a factor of gamma here. And it's quite a high factor. And so when we transform these accelerations, we end up getting a huge boost here. And so how can this be? That we have we have a strong Lorentz transformations in the acceleration, but this total power ends up being equal. And so part of this, we want to look at the angular distribution here, just to see what's actually going on. And so the instantaneous in the instantaneous frame K prime, we have some infinitesimal energy here. We have a solid angle. This tiny solid angle, we can divide it into our theta and our phi. And so we have some directionality here. And so we have this tiny little piece of the solid angle, which looks like that. We have a little bit of work. Actually, it's in the K prime frame. So it's this version of that. And what we want to do is transform each of these things. All right. So we can make some substitutions. And so we have this equals this, and this equals this. We also have then this thing is equal to du d phi, and this thing is equal to du prime d phi prime. And this simplifies everything a little bit. And so we have that this change in work is equal to this change in work here, prime, times our gamma factor, but there's an extra factor here, which comes from the energy momentum form of the 4-vector. Where we have this, because this thing was traveling in the x direction, we have this extra component of the momentum here, which comes from, where is it? Oh, it's back in the other lecture. Nope. Where did I go? Yeah. Right, so this is, where is it? All right. yeah, well, I guess it ends up being this thing. Okay, so where was I? Okay, yeah. So we have this derivative here and times this velocity to make it work. So here we had, I keep getting that confused. Here, there we go. We had this thing here was our x component of dw dt, and so if we multiply it by, if we don't take this we multiply by dt, we get this dpx here, and so that's what we end up getting here. And we end up having it be times a velocity component. Is that right? I think there must be a velocity component missing here, if I'm not mistaken. Is that right? Oh, so momentum has v. Okay, that's right. And then this thing would be energy. Would this have the same units? No. Now I got myself confused a little bit. Let's see. So this has. What units does this have? Sorry. I'm getting. Yeah, I'm puzzled by that. There should be an extra factor in one of these two. To get rid of it. I think there needs to be a velocity here. 1 over velocity. All right, let me come back to that. I may have to change that. But I'm pretty sure that in terms of unit dimension analysis, that has to be. Okay. Nonetheless, this, yeah, so this would then be this velocity, and this would be more or less correct in terms of units at least. So this thing, if we evaluate this out, this is our Doppler formalism, and so we end up sort of converting from our dw prime, I should put this in bigger form, to dw with a gamma and a Doppler factor here. Or rather, the relativistic Doppler factor is this whole thing. And so instead of just having this transformation here, we end up having a Doppler boost as well. Okay, so we can then look at this angular version here. So we have a transformation of our different angles from one to the other with this somewhat complicated nomenclature, which we had talked about, I think, 2 lectures ago. And so this, we can all, once we do the substitution for here, this thing then transforms like this. And there's significant math to go from here to here, but at least it sort of elegantly works out. That you have this nice transformation between angles, which just depends on beta. We can differentiate this functional form, so we get du and du prime, right, which we need for this transformation. And so the differential forms look like this, and so you have complicated sort of square version of this Doppler factor in both of these cases. And so this thing looks like this thing transforms like this as well. And the rotation around phi doesn't need a transformation. Right? So this d phi to d phi prime is fine. And so if we substitute back in here the dependence, so this thing is a function of the omega, and this thing is a function of omega, we end up with this extra two factors here, in addition to this factor. And so we end up having three Doppler factors, essentially, that come into play. And so if we want to get this power, right, to get this sort of power, we can use this change with time. And so we have to be careful because we have to figure out what time we actually are measuring. And so there are two possible choices here. And so one time is this conversion here. And this is the time interval during which the emission occurs in the K-frame. And this particular version yields the emitted power, right? And then there's a second time, which is the arrival time. And so that's the time of arrival of the radiation received by us in our frame. And so these differ by this factor here. And so this extra factor is due to the delay or the retardation effect of the moving source. And so this is the power received. And what is interesting is that the power emitted and the power received are not necessarily equal, but they're modified by this Doppler factor. So we can calculate the power emitted per unit solid angle or the power received per unit solid angle. And these end up being related by 3 powers of this thing for the emitted, 4 powers of this thing for the received, times this thing. And so we end up having something which looks like that or like this. So if we convert between U prime and U, for instance. And so the question actually is why do we have to, and which do we use? And so this is obviously the one that we observe. And so that's the most natural one for us to use. And so there's also a nice symmetry here of having 4 powers of gamma and 4 powers of this 1 minus beta mu term, which is a little bit more convenient to remember. So we can do, we just interchange the primes and the unprimed variables here. And we want to go between these two and change the sign of beta. And so this reason, this is also the most commonly seen and used. But this has its uses when you want to sort of understand what was actually seen or what was actually emitted by the source. You want to calculate this. And so if you can break it out and divide by this factor, you can understand what was actually emitted when you transform frames. Okay, so that's a lot to take in, for sure. So we also want to look at so let's imagine that we have a source which emitted isotropically. And so it emits isotropically in its frame, and we want to see what the observer sees. And so we have we did the relativistic boosting a couple of lectures ago. And so when we transform from isotropic radiation in one frame to what's actually going to be observed in the observer frame, this ends up being highly peaked in one direction, the forward direction, for very highly relativistic velocities. And so this thing, which is cosine theta, this thing, theta ends up becoming very small. You can make a small angle approximation, which looks like this. Beta looks like this. You can make a small, approximation, and with a Taylor expansion, it looks like this. And so this thing here will end up looking like this. And so we have a very strong sort of directionality or boosting that happens from this in certain solid angles. And so this ends up being very sharply peaked around theta equals 0, right? And so when theta is something non-zero, this term goes as the 6th power. And so you strongly diminish any radiation that's outside of theta. And so this thing has an angular distribution which goes as 1 over gamma. Right, so this product is what's dominating here. And so you will take all of the isotropic radiation and converge 50% of that into an angle which is proportional to 1 over theta. So if we think about this beaming case, and we go back to our particle here, and we have our K prime frame, we have the angular distribution of power, and this angular distribution of power looks like this. Coming back to our classical Larmor radiation. And so it has a decently strong dipole dependence here, right? And so this angle here is between the acceleration and the direction of emission. And we can write our acceleration in terms of parallel and perpendicular components. And we have something that then looks like this. So when we transform this thing and we divide this into our different components, we have the total power per solid angle has a fairly strong dependence, and we haven't converted this yet. We've just converted the A prime to A. And so we have a very strong boost here from this, but divided by this Doppler factor 4. Okay, so we then want to, so this is our angle theta prime, and this is our phi prime, this is our phi prime and theta prime here. And so this is the acceleration. This is the velocity of the 2 different frames, and the radiation is coming somewhere like this. So that's the mental picture. We want to transform this into our frame. So how do we actually transform this thing is the trick. And so we want to think about we're going to assess the received power, the angular distribution of the received power. And so we can think of a couple of generic cases here that will give you intuition on how to do this. So let's imagine we have a situation where the acceleration is parallel to the velocity. All right, so this is the situation. Acceleration is parallel to the velocity of the frames. And so in this case, the radiation looks like this, so it has this form. So the dipole is strongest perpendicular to this component. And so in this case, this thing is just equal to theta, and then this thing will then be equal to, or the transform of this sine squared theta, or capital theta prime, is equal to sine squared theta divided by this thing here. And this just comes from the transform of theta. from theta prime to theta. The perpendicular component here we have is 0. And so the parallel component is all we really care about. And so our parallel component of power is a function of this solid angle, right? So this is 0. So back here, this is 0. And so we end up having a transform that looks like this. And so it depends on a squared as usual. It depends on sine squared as usual, but we have this extra factor, this relativistic boost, which is going to the 6th power. 2 powers come from here, and 4 powers come from here. And the gamma squareds over here, and the gamma squared from here divide out. So this is one limiting case. We could have another limiting case, which is that the acceleration was perpendicular to the velocity. So, it's going, we have something which is maybe going in a circle, or orbiting, and then we have the frames moving apart. And so in that sense, right, at this particular component, we have this acceleration, and so the dipole is going in this direction. And whoops, here then, this thing, this sine theta prime would split out into sine theta prime and cosine phi prime. And so this thing would end up, when we transform sine theta prime, this thing doesn't transform. So we just square it, so we get the squared. But we transform this, and so we end up getting this. And so, well, we have the 1 minus this in the end. But that's how these things should transform. So we still have the same sort of functional dependency, but we have an extra cosine squared phi term here. Now the perpendicular component is 0. And so we're just caring about the parallel component is 0. So we're just caring about the perpendicular component of the power. And so we just have this component. There's no gamma here. And the gamma actually comes in here. So it's in this thing here, this beast. And we have this outside. So this is a bit uglier. So what do these actually do? So this is what we had in the original frame, or this frame. And so if we then consider a relativistic case where this is much, much greater than 0, sorry, much greater than 1. And so this thing, 1 minus beta u, becomes very, very small in the forward direction. And so this thing we can approximate by this. And so the two cases, this one then becomes something which looks like this. So it goes as gamma to the 10, and then another gamma squared theta here divided by this thing. And then the perpendicular component in the other case goes as something like that. So again, gamma to the 8. And so what you have is that this thing will transform to look like that. And so these two lobes, the dipoles, which were going out perpendicular, are now folded in and are within a beam of approximately, this angle is approximately 1 over gamma. In the other case, the perpendicular case, you have that this thing is, so this is with the velocity this equals 0, this is with the velocity equals 1, or beta b divided by c. So now here, this case, you strongly boost this, but you also fold these back in. And so you have something where even the emission going away from you is now partially going towards you. And again, half of the half of this hemisphere is going within a beam of 1 over gamma. So you get very, very strong boosting effects here as you get to the extreme relativistic cases. Okay, I think I will stop there. I think that's probably enough. Yeah, or should we just finish it? What do you think? You okay? No, I'll come back and talk about this on the next lecture. Okay, any questions?
I have a
No?
question. Yes. I have a question regarding to the emission spectrum from the retarded potentials.
Yeah.
I was wondering if in the highly relativistic regime we only take into account the y component, because I know I'm not completely sure if we only consider the y component because it's too much greater than the x component, or if or maybe if there are some other reason why we choose this component.
Let me see where.
Is the previous couple of slides,
Yeah.
previous presentation?
Okay. Uh, uh, uh,
Here, yes.
yeah.
So I was wondering if in the case of a non-highly relativistic case, we need to take into account the electric field in x and y directions.
Well, so I mean, this is just splitting it out so it's actually easy. What you would really want to do is do the parallel and perpendicular components as we did before. But it depends on how long you're integrating over. Right, because you will see this component and this component, sort of, but they will cancel out over the course of this trajectory. And again, the maximum, as you say, this is going to be smaller than this by a factor of gamma. And so, yeah, for highly relativistic cases, you can pretty much just focus on this one. It will dominate. And it simplifies things quite a bit.
So that means that in the case of a non-highly relativistic regime, we need to take into account both contributions?
In the non-highly relativistic regime. So I mean, say this is 1.5. Then, then there's not such a huge difference between these two. And so you will see a modulation over time. And so the total amount that you integrate from negative t to positive t will just be the y component. But there will be a temporal shift, which you'll see because you'll also see the x component.
Okay, I understand. Thank you.
But I mean, also it also depends on the orientation of this. So you're going to have to factor in, where's the observer in this picture too. So there are certain situations where you may not see the x, you may only see the y, or vice versa. Where you're talking, you're muted.
Hello.
You have a question?
Yes, I am still interested in the derivative of the acceleration. Is there experimental data about it? Of course, theoretically, we can continue derivating, right?
Yeah.
But how about the experimental data?
I mean, yeah, sure. If you have a change in acceleration, you can do that. You need a process which gives you a change in acceleration. You can, in the lab, you can make something which might do that. So, for instance, you could have something where you have an electron or positron or whatever moving through a field, and the magnetic field increases with X or something, right? So you could devise a scenario where you were changing the force on it. And so you could then change the acceleration. So I don't know in particular what experiments have you done in that sense, but I mean, I think you could feasibly make a experimental design where you looked at it. I don't know what you would gain from that other than demonstrating that it worked. But yeah, maybe you could look at how the particle radiated under such a condition. Yeah, but it's just it's a more complex equation of motion. That's all it is. But things like that do exist.
Thank you.
Yeah. You would, I mean, ultimately what you would do is just plug that in and you'd have to integrate over it. Right? Okay. Okay, any other questions? No? Questions from people I never hear from? Twyla, how are you? How are you doing? You following things? Okay. Santiago, okay? Okay. All right, if that's the case, then I'll see you guys on Wednesday. Yeah. Okay. Joe.
Goodbye. Take care.
Perfect.